This is going to be a fairly technical video where I'm going to be talking about this sort of abstraction that we have called the PII thermal circuit. Really quick before I get into that, I just wanted to go over some sort of like very basic theory of science type of stuff really quickly, just because we want this video to be, this is going to be already known by many people probably who watch this, but we want to be able to use this to show to people with lots of different backgrounds who are sort of wondering what the PII thermal circuit is. I'm going to be using the word abstraction a lot when I'm talking about the PII thermal circuit. And that's a word that's used in a very specific way in science and engineering and related fields. Basically, at the core of all science, you just have raw data, right? So just things that you've observed, but you can't use that raw data to do useful things. So we create abstractions from it, which is you're just looking through all that data to find patterns, and from those patterns you come up with, abstractions, or a lot of times they're called laws or theories. And those are oftentimes a series of simple equations or more complex algorithms or something like that. And then once you have this sort of pattern that has repeated in all the data that you've ever observed, you can use that to predict the future, essentially, to make useful devices or predictions or whatever it might be, because it's always been true in all the data that you've ever observed. That can be broadened a little bit in programming. You have things like, ultimately all that's really happening in a computer is you have this series of data and instructions which is going into a processor, which is putting those into electronics components that, just due to those electrical properties, has a certain result. So you have 8 pins going into some electronic component, depending on which wires have a current going through them and which don't, you'll get a varying result that is always predictable, always repeated exactly the same depending on which signals are on and which are off. And then you have abstractions on top of that, which would be like a function, which is written in something that's readable to humans, which is like add 2 floats, and you have 1 and 3 and you get 4 out of it. But that's an abstraction that is always true based on more fundamental abstractions that are based directly off of data. So you're just stacking these abstractions to make it something that a human is capable of going off of in the work that they're doing, even though the real ultimate truth that is eventually just pure data. That took longer than I wanted to. Maybe we'll cut some of that out. The reason why that's important is because I always refer to the PII thermal circuit as just a simple abstraction. And we thought a while about not releasing this publicly, and in hindsight maybe it's a bad idea to do, because we use a lot of a lot of techno babble in it. And I think the problem is that there's a lot of, for people who are just getting introduced to our project that don't know us, anyone who's been in the space of energy, particularly sustainable energy, and you look at all these different things that are presented, there's a lot of scams out there. There's perpetual motion machines, there's lots of things that make impossible claims. And so when you're claiming that you've made something which takes a very big leap forward in terms of its capabilities over previous technology, it's understandable that there's a lot of people who come in with a suspicious eye. And when you use this sort of technobabble that we use and these new terms, like we have this PII thermal circuit thing, it might have caused us more problems to release it publicly than it was worth, because it makes our technology, it makes the Tenkiv nexus seem much more complex than it really is if you describe it in practical terms that most people are familiar with. So what I'm going to do in this video is I'm going to go through all of the properties of the PII thermal circuit, and I'm going to read the very intentionally sort of theoretical phrasing of the property, and then I'm going to describe the practical implications of that. So first of all, PII thermal circuit stands for phasic integrated isolation thermal circuit. Phasic, integrated, and isolation are 3 important parts that we'll see in the properties of the PII thermal circuit. Basically what it describes, and I'm just going to read it directly off of our page about the PII thermal circuit that we have in the tech briefing, which I guess we'll link in this video, is a minimal set of structural properties that, if perfectly implemented in a theoretical device, would gather, transfer, and deliver thermal energy throughout a variable system at maximum thermodynamically attainable efficiency. So basically the situations that the PII thermal circuit are useful for is any time that you have not just, so let's start with just one part of it. You want to gather as much of the heat that's available at the place that it's being added as you possibly can. You want to lose as little of it as possible along the way, and you want to take it all out where it's going. But it's not just that. It's you want to have a whole bunch of places where heat's being added, a whole bunch of places where heat's being removed, and you want it to. So this is what we mean by variable system. That these same properties would work regardless of how many of these sort of nodes you add for places where heat's being added and places where heat's being removed. And you want it, so this wouldn't be for example, if you're just making a heat sink and you're just trying to cool something off. I mean, you could use aspects of this, but I wouldn't really call it the PII thermal circuit at that point. Again, the idea is moving heat from from many places to many places with minimal losses. None of these individual things are new. There's nothing where like we've discovered some new law of thermodynamics or something like that. I don't think that's going to happen, and I think that's part of the problem is people misinterpret what we're saying here. Really common things that you can compare it to would be like a heat engine cycle, like the Carnot cycle, or just a standard for electrical circuits like AC or DC or something like that, right? I think the easiest way now is to just go through the properties one by one and explain the practical implications of them. So the first property is one continuously integratable pressure vessel. We use the word integratable here instead of integrated because it can change. So you could have nodes being added and removed dynamically while it's running, but they're all integratable, right? Pressure vessel because it's comprised of two sort of layers is a way to think about it, and we'll get into the second layer in property 2, but the inner layer is a pressure vessel, just it holds pressure. That is P, filled with no other fluid than a dedicated heat transfer fluid. That's important because all the heat transfer in the PII thermal circuit occurs through phase change. So if you had some air from the atmosphere leaking into this internal pressure vessel, and then you had some water, it would boil at that liquid would boil at a specific temperature associated with the pressure of however much air has leaked into it. Whereas if you only have this dedicated heat transfer fluid, like you fill it solely with water or you fill it solely with propylene glycol or something, and this pressure vessel is completely the perfect pressure vessel, so it's maintaining that internal pressure. It's ensuring that nothing from the external environment affects the pressure inside of that vessel. Then that liquid will boil anytime heat is added. So such that in P intersystem heat transfer surfaces that are adding heat to the circuit, I.e. F is in the liquid or lower energy state. So by the way, this property is by far cramming the most in, so it might sound a little jarbled, but basically it has to be in the liquid state where heat's being added. It'll boil anytime heat's added because you have this perfect pressure vessel filled with only this dedicated heat transfer fluid. So it's not like water boils at 100 C. It's always boiling. It's not increasing in temperature when heat's added, it's boiling. All right, property 2. P is maximally thermally isolated from the environment. This is very simple, and I like properties like this because it sort of gets across what this is. So the PII thermal circuit is based almost entirely just on the laws of thermodynamics, but it sort of gives us these structural properties that we can use internally to build up all of their modules and the Tenkiv nexus as a whole itself, and have this common reference to go off of in order to try to get as close to this theoretical maximum as we can. You can always convert anything to heat with 100% efficiency, and it's not hard. So where your efficiency losses come in are when you're moving heat around, storing it, and converting it, and you're trying to ensure that during this transfer process, you have minimal losses. And even in the thing that's collecting the heat from another source itself, so if it's a solar panel, making sure that when you get up to these higher temperatures, you're losing as little heat as possible. So this is just describing that, maximally thermally isolated from the environment. In practice, this comes about through things like vacuum insulation and radiation shielding and things like this to ensure that all of that heat is staying inside of the thing that's meant to be collecting the heat and staying inside of all the heat distribution grid that's moving that heat around. The boundaries of P along I all are as thin as possible and as thermally conductive as possible. So P, by the way, is the continuously integratable pressure vessel, so the sort of inner part that actually houses all of the thermal energy. So first of all, if you had a very poor conductor and a very thick P, so the opposite of what this property dictates you need to have, you're going to have a problem where the outer part of the thermal absorber is much hotter than by the time it actually gets to the heat transfer fluid. And anytime you have a temperature differential in a thermal system, you have a lower efficiency than you could have, because you want everything to be only as hot as whatever is using the energy, because you always have higher losses when you have higher temperatures. And if you're not using those higher temperatures, there's no point in having those higher losses. This is just saying that in order to avoid that, you need as thin and maximally thermally conductive material. And this is a point where it's good to point out that the PII thermal circuit is a theoretical maximum, and this is a case where we actually intentionally don't implement it, because in practice, when you have a very thin material, for example, like a half or a millimeter thick piece of steel, and on the other side of it you have this heat transfer fluid, it's essentially instantaneously transferred through that steel anyway, even though steel is not a very good thermal conductor. You'd prefer something like copper or aluminum. Because it's so thin, you get almost no gains out of having a more conductive material. So again, this is meant to be pointing out the theoretical maximums, and not necessarily what we use in the Tenkiv nexus and all of the practical decisions that we make. The maximum possible area of all P inter-system heat transfer surfaces, I all, are in contact with F. Again, let's look at the practical example of a solar collector. If you have a collector surface, you can't have, for example, it's done in a lot of cases, you have this big chunk of like copper or something, right? And then you have this tube that's sort of snaking through it. Again, this is the exact same issue as with property 3, where you have a situation where parts of it are much hotter than other parts, which means that not everything is the same temperature as the use case. So you need full fluid contact in all heat transfer surfaces to ensure that you're reducing those temperature differentials. The distance between a P inter-system heat transfer surface, IX, and IX must be minimal. This is another one that the vast majority of the time, this isn't a real practical issue. But it's again good to keep in mind in the designs of practical systems, because if you were to have a solar collector in your backyard and you're trying to move that heat into a heat engine which is in your garage, which is 5 meters away. If you had some giant spiral that's like 5 kilometers long that you went through before you actually sent the heat to that heat engine in your garage, you're going to end up having losses there. You're going to build up pressure differentials, you're going to build up temperature differentials, and you're going to have unnecessary losses. In 99.999% of cases, this isn't a real issue. But again, it's just keeping in mind that any sort of design process that you have for when you're doing an installation or anything like that, you want to optimize shortest possible transfer paths. 6, F must be maximally restricted from flowing in unproductive directions. The classic example that I like to use for this one is, let's say you have a solar collector. During the day, it's collecting lots of heat, and then at nighttime, it's not. But let's say you drain all the liquid out of the collector, and again, this comes back to it being an integratable system, not an integrated system, right? So what'll happen is now you're powering all of these components through a different heat source. So now your provider is no longer the solar collector. And you still have all these consumers that you want to power, so you're pulling from, just as an example, again, a storage tank. Heat is going to flow to those solar collectors unless it's prohibited somehow. So you want to essentially de-integrate the solar collectors for that time from the rest of the system, going back to the property 1 where it's referenced as an integratable system, because otherwise it's just going to be losing heat, but it's not productive. You don't want heat to be going to those solar collectors. Property 7, pressure differentials throughout the system must be limited to originate from and be consistent with IX. IX is the heat transfer surfaces. If you had for example, a vapor manifold that was too narrow, what'll happen is it's very important that all the pressure be the exact vapor pressure of your heat transfer fluid. So if you're artificially restricting that pressure, it builds up temperature differentials throughout your system. Like almost a big part of lots of these properties are making sure that you don't build up temperature differentials. The practical implications are making sure that you are always looking at the sizes of any vapor manifolds or things like that, or even the space of the bodies that house liquids, and making sure that when that's boiling there's adequate space for it to move, so you're not artificially restricting that pressure. That's it. It's a lot to go through, and again, this is part of the reason why we thought maybe we should have kept it internal. This project originally started as a research project. Basically, we wanted to see if we could have a sustainable energy platform that was as applicable as fossil fuels to as many situations and was cheaper without any sorts of subsidies. Then it sort of evolved into, we wanted to see how cheap we could make it in general. and while still having that broad applicability. And in order to really achieve that goal of the research project, we couldn't iterate off of some existing technology. So we couldn't say like, these are the solar thermal collectors that are out there now, or these are the photovoltaic collectors that are out there now. Let's take them and see how we can improve them. But that causes a lot of challenges because you have this team of people that's trying to work together to make an actual physical device. And so the first thing that we needed to do is sort of see, okay, well, what would be perfection? What properties would result in the perfect system? And obviously we can't do that. It's not possible for us to make a perfect system. But then given those properties that would result in a perfect system, how close can we actually get? And always keeping those in mind with every design decision that we're making in the main system and all the modules and everything else, and trying to match it as closely as possible. So it basically gave us a target, if you want to think of it that way. As opposed to our target being a physical device that's out there today, our target was these sort of theoretical set of properties that we derived from basic thermodynamics. We didn't actually initially say this had to be a thermal system. If you're really going after some sort of theoretical ideal, thermal system makes the most sense, because using a thermal system, there's a lot of things that require very low quality energy. For example, just low temperature heating a room or a pool or something. You always want to keep the energy as low quality as you can for the use case, just like I was talking about with temperature differentials. And a thermal system allows you to do that very easily. You can just directly make low quality energy for things that need it and only convert to a higher quality energy when it's necessary. So you get higher temperature heat and you convert it to electricity or something like that. Whereas if you're not using a thermal system, you are always dealing with a higher quality energy. You don't have a choice there. And then if you want to make low quality energy, you have to down convert. So you're always taking these losses, even when it's not necessary. That's a not so brief overview of the PI thermal circuit, but hopefully it at least explains the reason why we came up with the PI thermal circuit and how we use it. So what I like to say, because a lot of times we get these questions like when you're in a VC pitch or something like that, and they say, summarize what's unique about your system. But that's hard for us to do for the work that we're doing. And what I like to say is, if you really want to know what's unique about it, it is the combination of all 7 of the properties in the PI thermal circuit. Individually, there is nothing that no one's thought of before. But again, coming up with this sort of theoretical maximum target and implementing it as closely as possible is what's unique about our system, and it is what has allowed us to reach such higher performance than anything that is out there today. Yeah, if there's any questions, post it in our forum, tenkiv.com. There's a forum link in there, and I'll go through and try to answer them. Or if I need to do another video to clarify a particular point, or maybe doing an entropy video on the quality of energy thing I was touching on briefly, I'd be happy to do that eventually as well. So yeah, that's it. Thanks for watching.